Hello, everybody, to our control lecture double, so to say, today. So, what did we do last time? We actually talked about closing the loop, right? Talking about what happens if we have a system and we're going to augment this system with a controller, and we need a measurement. We feed that measurement back. We plug the measurement or the error basically into our controller. And then we have a new system, right? So our original system, just the system itself. We have a new system, the so-called closed loop, where we have the system multiplied by controller and a loop around. That's what we call a closed loop. Okay, so we said, okay, if we have only the system, right, we have one input, one output. But if we have two elements in our control loop, we can look at various transfer functions. So we covered that. We said, okay, there's the complementary sensitivity, which is, I think, the most natural one, looking from the demanded input to the output. But we could also look at the sensitivity function, right? So how is the error influenced? And the other two were the disturbance sensitivity. So what actually happens when we have disturbances like wind on a car or an aircraft? What does that wind do with our output? And finally, we had the controller sensitivity, which we like to analyze for our control input, right? Because in reality, we will have electric motors, hydraulic cylinders, which are limited. So we look at this transfer function. Bottom line was, we know now 4 important transfer functions we can look at and we can analyze the system. We also figured all these transfer functions, I'm hop over, that you actually know what I'm talking about, have the same denominator, right? And we realized the denominator basically describes our poles, which correspond to the eigenbehavior of our system, right? What's different is just the numerator, which is basically how the input influences the output. And obviously, if we take a look at different channels, we always have a different input or a different output. Okay, so what's up for this long day today? The good news is tomorrow is a holiday, so we can go full speed. No, just kidding. Yeah, basically, it's kind of twofold today. In the first part, in the morning, we're going to look at the PID controller, the PID control elements, and what this PID controller is doing to our control loop. Because so far we know to what transfer function we look at, but we still don't understand why is it actually PID and not P or PI. And you should realize from the espresso machine lab exercise that with a proportional controller on a proportional system, we are not getting steady state accuracy, meaning that our espresso machine never reached 96 degrees. So that's not good, right? So, and here other parts of the PID controller will come into play, and we will take a look at different system augmented with the PID controller. And then I will guide you through, and it's basically, not much to write down in this first part because I will just show you examples of the PID control elements and what they do to the system, right? And in the second part, we then will have an understanding what part of the PID controller is doing what to our system in a closed loop. What then remains is what numerical values do we take for the PID controller, right? So the design problem is basically twofold. First, you have to say, okay, what's the structure of my controller for a given problem? So do I take a P controller? Do I do PID? Do I do PI? Whatever, right? So I will give you in the morning a roadmap which you can go through to decide which controller would be good. So you have decided for the controller, and then you need to set numerical values because the controller is fully free of your choice, right? You can select the structure of the transfer function and you can select the numerical values. And this is basically what we do in the rest of the semester. We figure out how it makes sense to select the controller that our closed loop behaves as we want, right? If, for example, if you design a car which should drive in the middle, if the If the road goes to the right, you don't want your car turn left, right? So this would be not a good control design. Or you don't want to have like 3 meters deviation from that, right? So this is how you select the controller. You need to set the controller. Okay, so let's talk about the PID controller and what its elements are and what the PID controller elements are doing to our closed loop. So, yeah, well, this is one more slide. I'm not sure if I finished with that one. Basically, what we are interested in, right? If we close the loop, we are interested, obviously, in the steady state behavior. For example, where is our final value going, right? But we are also interested in how is the dynamic behavior behaving, or how is the dynamic behavior. You figured with the espresso machine, when you turn up the gain too much, it started oscillating like hell, right? So we said, okay, we are overshooting to 130 degrees of temperature. This is not a good idea because the water will boil, right? So this is the eigenmotion is also influenced, right? So solving the how do we figure out what the characteristic how do we figure out how the dynamic behavior is in a closed loop? Well, we solve the characteristic equation, right? Same thing as we do for the open loop for only the system. We want to know if it's oscillating or not. We take a look at the poles or the eigenvalues. And then we look at the zeros to see what can also lead to some overshoots. Bottom line here is really that we now understand how a PID controller looks like, and we know how to analyze the closed loop model, right? We now know at what channels we're looking at. The next point is, what is the use of these individual controller elements, right? What is the P doing? What is the I doing? What is the D doing? And then we come to the actual design questions later on, when we then target what controller do I take and what are the numerical values. But now we're going to focus on the PID controller itself, how it looks like and what it does to our closed loop. Okay. So a PID controller obviously has a proportional element, right? An integrating element, and a differentiating element. That's what the letters stand for. Okay, so let's dig a little bit deeper into that. If you just say, okay, I'll take my PID controller, and you know how it looks like from last lecture, it's this, I think we called it R of S, right? And the input is the control error, and the output is the control command to our system. So let's do a simple thing. Let's just apply a step for E of S. So let's say E of T is going to be a step input, sigma. Okay, should not be that surprising how that looks like. The P element, okay, I actually could write down how this R of S looks like, right? We have a proportional gain plus an integral gain plus S times KD, a differentiating element. Okay, so obviously if the input, the control error is a step, the proportional part actually just is a pure proportional system, like we introduced it in the, I think, second lecture at the beginning, right? If we have a step input and this goes through the integrating element, well, it just integrates up our step, so it looks like this. And the differentiating element, this is more interesting actually. We said this is actually not really feasible, or we cannot implement that one. So we're actually going to use, instead of a D element, a DT1 element. So it actually looks like this, right? Plus 1. And then if you look at the step response, well, it starts somewhere and goes to 0. Why does it go to 0? Well, it's a differentiating element. Our input is constant after the initial time, and when you build the derivative of a constant, it gets to 0, right? So this is how a PID controller behaves. Well, let's say the elements of a PID controller behave. Obviously, if you add up, because we have a plus here, you need to add up all these three things together. And your job as a control engineer is now to decide which of those elements do I actually need, right? Because it's not always said that you actually need all the three, or differently, sometimes it's not possible actually to use all of those three because of stability, right? But we will see that later. Okay, so however, that what I've just shown you obviously is just what happens if you look at the controller alone, right? So you look at just this isolated element. But obviously, where I have some space, what we are interested in is actually the closed loop, right? So we have this PID controller R of S, we have a system G of S, and what we are interested in as engineers is the closed loop. So we are not only interested in that element, but we are interested in our behavior from R to our output Y. So how is our reference transferred to the output Y? So this obviously makes sense to look at just to understand the pure PID controller. But now, next thing is we need to look at what happens if we use a PID controller in a closed loop, right? And what I'm going to do is we're going to take two systems, actually very simple systems, but systems which are very common in practice. We take a proportional system with a first order lag, so a PT1, and then we take an integrating system, an IT1 system. So we have a free integrator. You have seen with the examples we did, also integrating systems are quite common. Think of the bathtub we had, or if you have an actuator and you look from the current to the rod position, you're integrating that up. Think of a simple car. If you push the gas pedal, the position of the car always gets more, right? So it's basically an integrating behavior. So we take these two systems and then we plug the elements of the PID controller around, but one after the other, and see what happens, okay? So let's talk about these two systems we're going to look at. So the first system is a simple, so okay, let me write this down one more time. So we take a system G, and in our case, it's going to be a PD1 system or an ID1 system, and we take the different elements of the PID controller and plug that around and see and take a look how these elements influence our closed loop, right? So we're going to look at how our reference is transformed to the output and maybe also the disturbance sensitivity. So maybe a good idea would be to look at T of S, the complementary sensitivity function. Okay, so this is the job for the next half an hour. Okay, the first order proportional system looks like this. So we have a gain, a static gain of 0.1. Here, what does that mean? You're getting only 50% of your input, right? So if you put in, 100, the steady state response will be 50. If you put in 25, the steady state response will be 12.5. So you're only getting 50%. This is what this means. Okay, the time constant is 0.75, which corresponds to a pole at minus 1.33. What does that mean? Well, that means that you need 95, to reach 95%, you need 3 times 0.35, which is probably 2.25 seconds, right? So this would be the interpretation. Okay, and then we're going to plug around the elements of a PID controller and see how the dynamics, so how is this pole changed and how are these 50% changed when we use a controller. Okay, in the second example I promised you is an integral system. So you have this free integrator here, multiplied with a PT1. An integrator multiplied with a PT1 is an integrating system with a first order lag. So what can we say here? Okay, our gain is 0.7. Take care, it does not have a steady state gain case 0, right? Because this is integrating. If you if you put in a step here, it integrates up to infinity. It has a pole at 0, it's this guy here, and it has a pole at -10, corresponding to a time constant of 10 seconds, right? Sorry, a time constant of 0.1 seconds, not 10. It's the negative inverse, so 0.1 second, which is here. Okay, so these are our two systems we're going to look at. And for the controller, for this guy, we're going to say this controller is going to be a PID. First, we're going to say, okay, this controller are only the elements of a PID controller. So we're going to first take the P, then we're going to take the I, and then we're going to take the D. And then we're going to take a look at the different channels, and specifically we're going to look at, let me mark this, how our, no, not razor, how our input is transferred to the output. And let me take a look how our disturbance is transferred to the output. So what we are going to look at is our T of S, so our closed loop transfer function from R to Y, and our disturbance sensitivity G of S times S of S, right? So how is a disturbance influencing the output Y of S? So these are the two things. Okay? Okay. So let's kick it off with a pure proportional controller. So we are just taking, where's my mouse? We are just taking the P element of our controller, right? We leave out the I and the D. So this is the closed loop transfer function, right? That's what we discussed last time. It's defining how our reference is transported to the output Y. And what's the usual design goal for that complementary sensitivity function? Think of the espresso machine in the lab exercise. You want to have this guy to be 1 in steady state. 1 means you're basically getting 100% of your input at the output. If you want to have 96 degrees, you're getting 96 degrees. But I guess you already figured with a proportional controller on a proportional system, this does not really work. But let's see. Okay. Obviously, the goal is that if we just wait long enough, this guy gets 1, because that means we're getting 100%, right? Okay, so the only thing we need to do is we need to plug in our KP here, and we need to plug in our system here, right? So the PD1 or the ID1. Okay, let's start out with the closed loop if we use the PT1 system from, so this guy here, right? So we close the loop with a proportional controller. Okay, if you do that, you can do that at home. On paper, it's actually not that hard. You end up with this PD1 system. So your closed loop is again a proportional system of first order. However, we are seeing something has changed, right? So somehow this proportional gain shows up here. So we basically changed the pole of the system, and we're changed the steady state behavior. And remember, the open loop has only 50%. If you take a look and you do the final value theorem, so you're looking at what happens if I let S go to 0, meaning that if you wait long enough, and then you get to this equation here, right? And you see this actually can never get 1, right? Because whatever you put in for KP, this will never be 1. So you can never reach 100%. You could say, okay, I can just make my proportional gain very big, right? So in the espresso machine example, we increased this gain from, I think, 0.02 to 0.6, and we moved closer to the final value. And this is what you see here, right? If I make KP, the bigger KP is, the bigger it is, the closer it is to 1. However, there you will run into other constraints. We figured for the espresso machine, if we make this Kp very large, we are getting oscillations like hell. So this is practically usually not possible to increase that gain too much, right? So there will be a limitation. Okay, let's take a look what happens for our integral system, right? If you close the loop over the integral system, you suddenly come up with this closed loop. And if you multiply that out and you make the final value theorem, the solution is 0.7 over Kp over 0.7 over Kp, and this is equal 1, right? Meaning that whatever Kp you select, right, you can put Kp anything but 0, right? Whatever you put in for Kp, it will get 1. So you will always reach 100%. And this is actually the fact is always true for integrating system. If you have an integrating system and you can only use a proportional controller, you will have perfect reference tracking. You will always get at the output what you want at the input. It works for integrating system. It does not work for proportional system. So this is the takeaway. So the bottom line is, for integrating systems, a proportional controller is able to track the step input with zero control error, whereas it is not possible in case of proportional systems, right? And this is actually always true. So this is important to remember, because thereby you can double check if you do examples. So we said, this was the first part, right? We said, okay, let's take a look at our transfer function from the input to the output. From the reference input, what we want as a pilot, as an engineer, or as espresso machine user, what do we put in and what do we get out, right? So next thing is, what is going on with disturbances? Think of a car, you can have like wind. Usually you don't know disturbances, right? But you want to know in the design process, how is that disturbance influencing my system? And the goal would be that the disturbance does not have an influence. Think of your car. You want to drive 100 kilometers per hour. You turn that switch on in your car and say, okay, please drive 100 kilometers per hour. And suddenly you have front wind. You still want to drive 100 kilometers per hour. This disturbance should not make your car drive 80 kilometers per hour now, right? So you want that actually to be zero in steady state, okay? So the disturbance sensitivity is this guy here. So it's a little bit different. We don't have the controller here. If you compare that, the closed loop, the complementary sensitivity has the controller here, the disturbance sensitivity not. And our design goal is clearly in steady state. If we just wait long enough, right? So we let S go to 0, this guy should be 0, because our car should still drive 100 kilometers per hour. Okay, so what happens to the disturbance sensitivity for our, in case of our proportional system, PD1? If you do the final value theorem, you see, okay, how it's not getting to 0, right? Obviously, if you make K, you make the gain bigger of your controller, it gets better, but it will never reach 0. This is kind of expected, right? We have a proportional system. We don't get perfect reference tracking with a proportional controller. We also don't get perfect disturbance attenuation with a proportional controller. So proportional controller for proportional systems, not a good choice. So more interesting probably is the integral system. For the integral system, we saw that we actually have perfect reference tracking with a proportional controller. However, we don't have perfect disturbance attenuation. See? This guy, again, will not get 0, whatever Kp you put in there. So, for proportional and integrating system, a steady state error of 0 for a constant disturbance input cannot be achieved. Okay, so where are we? We've talked about proportional controllers, and we now know a proportional controller works pretty well for the reference tracking if we have an integrating system. It does not work well for reference tracking for a proportional system, and it does not work for disturbance attenuation for both of those systems, right? Okay, so proportional controller is not always kind of a good idea, right? So this is the takeaway here. Okay, next thing is, no, not next thing, we're gonna talk about the dynamic behavior, right? So what's happening, now we've talked about what's happening in steady state, right? So when we wait long enough, but we said we also have a pole of our system. The pole of our PD1 system was at minus 1.3, and the pole of the integrating system was at minus 10. So what happens here? What happens to the dynamics if we have a proportional controller? And here I actually made you some figures in MATLAB. I took the PD1 system and changed the controller gain, right? So we already figured if we increase the gain, we are getting actually closer to the one in the reference channel. So this is getting better. What it also does, it gets faster, right? So the bigger the gain is, the faster it gets. And you have seen this with the espresso machine. Your answer got faster, however, it started oscillating. This was because we had a PD2 system. You know, a PD1 can never oscillate. This is what you see here. And for the disturbance, well, the disturbance sensitivity gets down, right? When we increase the gain, the disturbance rejection gets better. However, we never reach it 0, and it gets a little bit faster as well. Okay? This was for the proportional system. What happens with the integrating controller? Same thing, or not same thing. Here, it's notable that we always reach 100%, right? What I'm simulating here, by the way, is a step response. So I'm putting in a unit step response, which has a 1 at the input, so it reaches the 1, while in the proportional system, it does not reach equal 1. Here, we have perfect reference tracking. And when we increase the gain, it gets faster. However, this guy now starts to oscillate. Why is this guy oscillating? It's an integrating system with a first order lag. So we have two poles. What happens in a closed loop, and this is actually, you should be aware of. This now looks like it's not only looking like, it is a PD2 system. It's a proportional system of second order, sorry. Because we have two poles. Our system has two poles. It has a pole at 0 and it has a pole at minus 10. If we put a proportional controller around it, it gets a PD2. We are stabilizing our integrating system. So in a closed loop, we don't have an integrating system anymore. We have a stabilized proportional PD2 system, right? Okay. So, however, the disturbance rejection is not perfect. It's again, there's something remaining. If you increase the gain, it gets better. However, here, well, the oscillation is not very big, but it starts oscillating. Okay? So let's sum that up what we have for the proportional controller. It reacts to the controller error without delay, right? This is what you've seen here. I'm going to go back a couple of slides. Here, there is no delay, no lag in there. It immediately reacts because it's just a proportional gain. If you have a proportional system, it leaves always a steady state deviation. It will never get to 100%. So this is Naturgesetz. For integrating system, it makes your error between from a step input to your controlled variable to 0. It's always like that. However, for both systems, it is not possible to track to get the disturbance to 0. There will always remain some effect of the disturbance. That means if your car is a proportional system and you apply a proportional controller, it will not be able to get rid of this headwind. You need a different controller for that. And this is what a lot of you figured when they did the espresso machine example, whatever controller gain you put in, it will never reach the 96 degrees. You can make the situation better by making it bigger, but it will never get there. Okay, so let's go. Okay, so much for the proportional controller. Now let's take PID has 3 elements. Let's take the integral controller. And here something interesting happens, which we already can conclude from this proportional controller. You figured that when the system has an integral element, it's actually pretty good for reference tracking, right? And this is actually true for the controller. As soon as your controller has an integrator, it is able to track perfectly. So this is the key element you need to think about when you think about steady state accuracy, when you don't want to have any control error left in steady state. If you want to reach 96 degrees, and we're going to do that for the espresso example, we're going to assign a controller with an integral element. Why is this the case? I know at the beginning it's sometimes hard to understand why do I need an integrator, but actually it's pretty simple. What do you need that you have perfect reference tracking? Your reference input should be equal to the reference output, right? In the espresso machine example, if you put in 96 degrees, your output should be 96 degrees. So what does that mean for the control error? Your control error is going to get 0 if you have steady state accuracy, because reference input minus measurement needs to get 0. So taking that 0 and putting through a proportional controller, it's obviously going to be 0 again, because 0 times something constant is going to be 0. That means that you're going to apply a 0 input to your system. And in case of the espresso machine example, this is not going to hold, right? Because in the espresso machine, we had a room temperature which takes out the energy of our system. So if we put nothing in, if we don't heat the water, we will lose water temperature. So this is not going to be an equilibrium point of our system. So what we need is, we want to have 0 control error, but we still need an output. We still need an output of our controller or an input to our system. And this is only possible with an integrator, because the integral integrates the error over time, and still when the error is 0, the integrator will output something, right? Because it kind of remembers everything what happened in the past. This is what an integrator does. You plug everything in your integrator, all the errors, and when the error is 0, you don't put anything into your integrator, but the integrator remembers. So what happens is, the integrator remembers what you need, which input you need to your espresso machine, how much power you need to have 0 control error. So I hope this is a little bit more intuitive than thinking about only the mathematics. Okay, so let's take an integral controller, which is nothing but this gain here we can set over S, right? So again, if we want to take a look at the steady state error, we take the reference tracking, so how we want that to be 1. So if you now build the closed loop system, taking the integral controller and your PD1 system, the closed loop looks like this, right? So your complementary sensitivity function for our PD1 system looks like this. So one thing to note here, you could say, wait, why do we have S squared here? It's in the open loop. Our system is a PD1 system. Why do we have now a PD2 system here? Well, you have a PD1 system, your system is PD1, but your controller also has a pole, right? So you have 2 poles. And these 2 poles get stabilized if we do it right in the closed loop, and are both going to be in the left-hand side, and are going to be, what the result is going to be a PD2 system, right? So one pole from the system, 1 pole from the controller. You add that, it's 2, it's a PD2. Okay, so if you do the final value theorem here for a step input, you let S go to 0 and you see the gain gets, whatever you select for your controller gain, this is going to be always 1. Okay, that's actually good. So we will see our espresso machine is actually a proportional system. If you design an integral controller for it, it's going to be steady state accurate. You will get 96 degrees at the output. So this would have been the solution you need. So what happens with the disturbances? Okay, let's stick with the PD1 and simply compute the disturbance sensitivity. Remember, we want to have the disturbance sensitivity to get 0 because we don't want to have any disturbances influencing our output at steady state. If you compute that transfer function, you see if you let S go to 0, you basically have a 0 here. This guy is always going to get 0. So we can say if you introduce an integrator to your system, you're adding additional dynamics. This is why you have a PD2 closed loop, right? Same, this is actually a DT2 for the disturbance sensitivity. You're adding dynamics, but this integrator makes your system accurate. So whenever your boss tells you, please design a controller which is steady state accurate, you need to think about an integrator. Okay, so let's stick around with the proportional system, with the PD1 system for a while, because we will see we will have some issues with an integral controller when we have an integrating system already. Okay, so let's talk about what's happening to the dynamics now, right? We said, okay, this slide I've just shown you talks about what's happening in steady state if we let S go to 0 or T go to infinity, meaning that what happens if we just wait long enough. But we also might be interested in the oscillatory behavior, because we are clearly seeing here this is a PD2 system, and we know a PD2 system can oscillate. So again, the same thing as before, we are taking a look at what happens if we change this controller gain Ki for our PT1 system. This is actually wrong here. So it's the fourth time I'm holding that lecture and never realized that this is actually wrong here. So please let me fix this for this has to be a PD1 behavior. So please fix that in your notes. I will do an update on that after the lecture. So what happens to our proportional system of first order if we close the loop? So what we see is that this guy always gets to 1, right? So we have steady state accuracy because of this integral in our system. But the problem is we cannot increase that very much, because as soon as we start increasing that gain here, it starts oscillating pretty fast. See, when we have a gain of 15 here, it's actually probably oscillating too much. It's not very good damped. So we are actually reaching an overshoot pretty fast. The disturbance, remember when we had just a proportional controller, this went out flat here. This did not go to 0. For all the control gains, this guy gets to 0. So this is actually pretty nice. For our proportional system, we do get the control error down when we have disturbances for all the control gains, whatever we take. And if we increase the gain, it gets better, but actually the oscillation gets a little bit bigger. So it gets faster, but you see the blue one is oscillating more than the yellow one or the magenta one, right? So you get more oscillations in. So if we compare that to the proportional controller, it's now steady state accurate, right? We get to 1, that's what we want. We get to 0. However, it's significantly slower. If you would compare this, the x-axis, you will see it's slower. We cannot turn up that gain. And this is actually an important takeaway for today. If you don't take anything from today's lecture, these two things you should take. If you want to have it steady state accurate, you need always an integrator. However, the drawback of an integrator, it's slow. A proportional controller is fast but not accurate. An integral controller makes your system slow but accurate. Now you could think of a solution. What would be accurate and fast? It's actually pretty simple. Okay, so the key takeaway here, your integral element makes your proportional system accurate. So now finally, let's talk about the integral controller for an integrating system. So if you actually compute the steady state value, or if you compute the complementary sensitivity function and you do the final value theorem, you actually turn out with a value of 1. But this is wrong. Remember the final value theorem? We said we are only allowed to compute it if the final value actually exists. And if you have an unstable system, the final value theorem will tell you the final value is 1, but you need to check stability. If your system is unstable, it goes to infinity, but the final value theorem is not applicable then, because the final value does not exist, right? The final value only exists for stable system. You can actually try that, but I show you the simulation to it. So the dynamic behavior for an integral system without differentiating elements, right? So it might be different if you have additional d terms in there. But if you just have ITN systems and you plug in an integrator, it's always going to be unstable. You cannot stabilize, or differently said, you cannot have two integrators in your system if the system is pure integrating and delayed. You'll see that in a second. So if you do the time simulation, depending on your case, this guys always go to infinite, right? So if you would wait long enough, this would just go to infinite. So although your final value theorem says, okay, here we have a value of 0 or 1, whatever transfer function you're looking at, you're not allowed to do that because it is unstable. It goes to infinity. You cannot trust the final value theorem. Actually, you are not allowed to apply it. You always need to double check the stability. Okay? So integrating system, adding another integrator is not always a good idea. You need to think about some differentiating elements. Okay? The core takeaway here should be, I need one integrator to make my system steady state accurate for step inputs. If I have two, so more is not always better here, right? The more integrators you put in, you will actually degrade your stability. Why is that? An intuitive explanation would be, we said, okay, an integrator, right? What is an integrator doing? It integrates up your error. It's slow. It takes time. And slow systems are always prone to instability. The perfect example for that is a broken shower. You go into the shower, you turn hot water on, it doesn't get hot. You turn it on more, it still is not hot. You turn it on more, there's a lot of delay in there, and suddenly it gets pretty hot and you're close to burn yourself. What you do, you put it to the other side to full cold, or let's say 90% cold. It's still not getting cold, it's still hot because of time delay. You make it even colder, and suddenly you have a bang to the other side and it's freezing, and you're kind of going, you're making situation worse, right? So time delay makes your control loop perform pretty bad. And this is actually what you introduce when you introduce an integrator. You introduce delay. lag, and this is actually a problem, right? You basically start to overcompensate because the reaction of the integrator is so slow, and this is actually what happens when you have two integrators. Situation is pretty bad. Okay. So let's sum up our integral behavior. It reacts with delay to the control error. You can go back to slide number, oh my god, what was the slide number 29? You see that it needs time to build up the control input, right? And this is actually the drawback of an integrator. The good thing about an integrator into your controller is, for proportional system, it makes your system steady state accurate. So for stepwise reference input, it controls your system to no error, and it mitigates all input disturbances. However, the control gain is limited. You cannot increase the control gain too much because it will start to oscillate. And it will always lead to an unstable behavior if you already have one integrator in your system and you don't have any zeros in there, right? Okay. So we covered now two of the three elements, right? We said PID controller, proportional gain, proportional element, integrating element. We know what this one is doing. And now we have the differentiating element, and actually you basically never use the differentiating element alone. So you will never hear, oh, I'm implementing a differential controller. This is really, really rare. We mostly talk about proportional controller, integrating controller, or combinations. Why is this pretty rare? Well, it's a differentiating element. Think of it, what a pure differentiating element would do. You put in a constant, and this constant is differentiated, it automatically gets zero. So this differentiating controller is not doing anything, it's just changing the dynamics, because when you have something constant as input, it will lead to no output. So it's only changing when you change the input variable. So it's kind of not really fair to talk about the controller here. So, because it has actually no effect in steady state, right? Remember, when we say in steady state, we always think of a step input, right? So your U of t is this. If you run that through a D or DT1 system, this actually kind of looks like this. So in steady state, this guy, well, actually you could write here E and here U of t, this guy gets zero because it's differentiating. So it's only changing the dynamical behavior. And this is actually what it is doing. You're using this differentiator in combination with proportional integral controllers or proportional controller or integral, no, not with integral controllers, to accelerate the system response, to damp the overshoot, and to stabilize unstable system. Remember, we said zeros are basically the counterpart of poles. While poles introduce lag, differentiators increase the speed of your system, because by differentiator, you are not only reacting to your input, but to the derivative of your input. So if your input is position, your controller would react not only to the position itself, but also to its derivative. The derivative of the position is speed. So you would also react to the velocity of your input, and this obviously should tell you it makes your system faster, right? Okay. Yeah. Yeah. This is just says that you don't actually use a ID controller, right? Because why doesn't it make sense to in pure ID controller? Because the I cancels the D, right? You would have S over S. It's again a P controller. Does not really make sense. Okay, so this is where we are. We know now what the each of the three elements of our PID controller is doing in a closed loop, right? We know what a P is doing. A proportional controller makes your system actually faster, but it's not accurate. Your integral controller makes your system accurate, but actually is pretty slow. And the differentiating term actually can help to increase the speed of your system, to damp the overshoots and so on, right? You're rarely going to use each of the elements alone. So the conclusion is, one of the most used controllers is the proportional integral controller. Why is that? Well, the proportional element is used to make your system faster, and the integral element is used to make your system accurate. So you're basically combining the positive things of two worlds. If you use a PID controller and your system is still too much overshooting, you use the differentiating element, because we know it can make things better, it can damp our system, it can accelerate our system even more. So, where I'm heading to is the following. You as engineer need to decide what controller you're taking. So what I wanted to develop, and it's actually one slide, it's a roadmap for you. You can look up when you do a project or whatever, where you say, okay, which controller should I take? You can look at this roadmap, right? And I want to go over this. So what elements of the PID controller should I take? So obviously the PID controller has certain variants, right? So the proportional controller reacts immediately, so it's fast, but it leaves you some error. An integral controller is accurate, but is slow. And this is why we're going to combine this to the PI controller, which is fast and accurate. So a PI controller is actually very often a good choice. If you figure out the PI controller, it still needs to be accelerated, and the oscillatory behavior shall be damped even more, you end up with a PID controller. So remember, PI is a good thing, PID if you want to make it faster. When would be a pure P controller a good idea? A pure P controller would be a good idea if you cannot introduce any integrals. Like we've seen with the integrating system, if you already have an integrator there, you can go along with a pure proportional controller. If you use a pure proportional controller because you have the integrator in the system and you say it's still slow, you use a PD controller because the D term accelerates your system, right? That would be actually the use case for a PD controller. Integral controllers, actually pure integral controllers, are rarely used because they are just too slow, right? We always take the advantage of the proportional element, and if we just make it small, it's still accelerating our system. So pure integral controllers are really, really rare. Okay, but yeah. The remainder of these slides are when leave out the integral element. You could say, okay, I don't care about steady state accuracy or disturbance suppression, right? Then you just leave it out, the integral element. But you still want to damp the system, then you need the D. And the second part, or the second idea when to use a PD controller, is when you just are not able to introduce an integral element because you already have some integral is in your system. What should not mean that if you have an integrator in your system, you cannot put in another integrator in your controller. So this is possible, but you need to compensate that with a lot of differentiators in your controller. So you could end up with a PID2T2 system, right? If you really need that by heart. The pure PID structure is not providing that to us, right? So, but these are rare cases, very specific cases. But we will do that later on. If we need more complex control than the PID, we will need to think about better design methods than a just thinking about the PID. Okay. Obviously, if you need to stabilize a system. So if your system is unstable, let's say you have a PT2 which is unstable and oscillating, you always need a D term in there because you cannot stabilize that system. So if your system is unstable, it's also always a good idea to think about the differentiating element in there. And actually in flight control, you sometimes have PD controllers, also in car control, where you mainly consider about your mainly job is to stabilize the system, like a Eurofighter, right? Eurofighter is it's an unstable system. You want to stabilize that. I think it has PD elements in there. Okay. I know that has been a lot now, but we are at the point where we kind of understand what the PID elements are doing and what the roadmap is to select the structure of a controller, because this is a problem, right? Or this is not a problem, but this is something we need to be aware of. We have PID controller, but we always need to use the PID controller. It's our job as engineers to decide what controller we use. If we're always going to use a PID controller, it's actually sometimes not going to work. So we have to dig deep into the system. We have to understand the system, and then we can design a controller. I mean, you can always say, okay, I don't care, my artificial intelligence algorithm is going to do that. But I tell you one thing from my experience, the AI will not solve your problem, and it will run at some point in problems, and then you still need to understand the system and fix it by yourself, right? So meaning that AI algorithms are not always that intelligent as the mathematicians claim, or the informatic guy claims. Okay, so actually I have 5 slides ready. Ready, yeah, I hope they're ready. I have 5 slides remaining, and on these 5 slides I want to simply show you some applications of the control, not really applications, but more like classifications of the controller. So basically we have discussed this already, but these are more to build up some intuitiveness, right? So if I tell you what is an integral controller doing, you immediately know it's steady state accurate. So I'm going to show you some tables on the steady state behavior, which we can classify, and then we're going to dig into what is actually changing with the what's happening with the dynamics of our system, right? Just some examples. Okay, and this is the remainder of the first lecture today. Okay, so if we want to sum up all of that, what we have discussed for proportional system, we can sum it up actually pretty nicely in a table. So why I'm doing this is simply because it's always the same if your system is a proportional element. So if your plant looks like this, right? So it's a proportional type, meaning that it has no free integrators 1 over S or free differentiating S. So we don't have a pole or a zero in the origin. It's simply proportional. It can have zeros. It's just not allowed to have those zeros in the origin. Okay. So we're going to take a proportional system, and we're going to take a look what is the proportional controller doing, what is the integral controller doing, and what is the PI controller doing. So the combination of these two in steady state, right? So for the steady state behavior. So if we just wait long enough. So you could say, why don't we look at the PID controller? Well, the D element, it does not make sense to talk about the D element in steady state, because we know the D element has no influence in steady state, because in steady state we have a constant. The derivative of a constant is 0, so no need for that here. Okay, we have seen, so we have these 3 different controllers, and we know our system is a proportional system. Okay, if this first column here tells you something about the complementary sensitivity, so what happens with our reference tracking? We know if we have an integral element, the reference tracking is perfect. Right? This is what we see here. For the proportional controller, it's not perfect. We are left with some control error. So far we only talked about step inputs. What happens if we have a ramp input? For a ramp input, your control error for a proportional controller will get to infinity. If you have an integrator in your system, so it may be a pure integral controller or PI controller, you will have a constant error in case of a ramp input, right? The last column then talks about what happens if you have a disturbance. Think of the car with the headwind. So, proportional controller for proportional system always gives you an error, meaning that your disturbance will introduce an error, an influence on your controlled variable. While for as soon as you have an integrating element, the disturbance gonna get to 0. Okay, so this is what this first part does. In the second part, we're gonna talk about integrating systems. So the only thing what changes in that thing here is that we now have a pure integrator here, right? This guy here is still proportional. We are adding a free integrator. So what we figured, whatever controller we are using here, a proportional or integrating, we are ending up with no control error, but be careful, this guy here is not stable. So this guy is unstable. If you have a ramp input, well, if you have a ramp input, a pure integral controller will still make that error to 0, but again, this is not stable here. Finally, for the disturbance, we know if we have an integral, it's going to get to 0. If we have a proportional controller for an integrating system, we are left with a control error due to the disturbance. Okay? So this is basically the summary for the steady state behavior. What happens if you have a proportional system? What happens if you have an integrating system and you have these 3 different controllers? So I try to cluster that for you as much as it gets, right? You should realize at this point every system is different and it's hard to cluster all physical systems in one. But a lot of engineering problems you will end up with proportional system. If you think of producing industry, they mainly have proportional system with lag, right? So this is always the only thing you need to look at. Flight control is a little bit different. That's the bad news. Yeah, the question in the chat we have, could you repeat what the K star was again? Yes, I could do that. This is new. I introduced that because last semester I had a question from a student and she said, okay, it would be easier if we use it uniformly because I figured I have different notations, so I introduced that. I guess you know what this K0 is, right? This K0 is the gain, is the static gain. So if you let S go to 0, this is what you're remaining with. So, and this K star is basically your K0 of the element without the 1 over S. Right? Because this guy, if you let S go to 0, goes to infinity. So I cannot write K0 here because K0 is infinite. So I'm writing K star. Just to have a, it's basically a K0, but of the element without the S. That's the only difference, right? So to determine K0 of a plant, G of S, which is proportional, you just put S to 0. You end up with the static gain. But here, if you put S to 0, it's going to get to infinite. So to still talk about this gain here, we are making this case 0 or this case star the case 0 of only the element without the 1 over s. Right? We will need that later when we go to the frequency domain, and yeah, and in the Bode diagram, and this is why I decided for that. So I'm actually not allowed to write here case 0 because it's not a static gain, right, so to say. Yeah. Okay, so this was the steady state behavior. On the next 2 slides, they are actually pretty full. Obviously, you don't need to remember that by heart, right? The next 2 slides are mainly for just to build some intuitiveness to understand. I mean, I could give you examples and let you calculate, but I don't think this is only one part. So on the next slides, I'm going to take a proportional system. In matter of fact, it is a PD2 system, and then I apply all different PID control variants we have, and we see what happens if we change the gain and so on. And on a slide after that, I'm going to take an integrating system with a first order lag, and again apply all the different controller variants, right? Just to give you some intuition what's actually happened when we close the loop. So let's start out. So we start out with our plant. Okay, let's actually write that here. What we are doing here. So what we're going to do, we take this PD2 system, GPT2, and we close the loop around with different controllers, right? Okay, and we now take a look what happens in that loop, right? So how is that new system behaving like? Controller multiplied by our system, which is a PD2, and then closing the loop. And for R, we take all different possibilities we have. So what do we have? We have a P, we have an I controller, we have a PI controller, we have a PD controller, and we have a PID controller. I think that's very much it. Yes, there are no more options than this. PD, PID. Again, ID controller does not really make sense because it's a proportional controller then. And yeah, that's it. Okay, so let's start out. Here you're seeing, is a pointer. We're seeing this second order system augmented with a proportional controller and with a, okay, let's start out with the proportional controller. So you see the full lines here are the complementary sensitivity. So how is my reference input transferred to the output? So what do we see here? We again see a proportional controller for a proportional system will leave us with some errors. So we never reach 100%. We never reach the 1 here. But if we increase the gain, we're getting closer. If we increase the gain, we're making our system faster, but at some point we're starting to overshoot, right? Remember, this is a PD2 system. We have a P controller, so it's a second order system, and we are changing the dynamics. So at some point, we're going to start to oscillate, while this guy is not oscillating. The dashed line here is for the disturbance. So obviously, these guys, we want to have 0. We don't want to have the influence of the disturbances in our loop, right? So that would mean, okay, let's write it in the loop. This is R to Y, and if we add a disturbance here, we look at D to Y, D to Y. These are the dashed lines, right? This is what you see here. We want to have no influence. It's getting smaller, but we never get it to 0. So what happens to be if instead of a proportional controller, we are using a D term, a PD controller? Well, same gains here, right? So you see, the PD controller is in gray. We are actually damping the system a little bit, so the oscillation gets smaller. You see it from here to here. we make it a little bit faster, so this is expected. We are using the D term. However, in steady state, nothing has changed, right? Because remember, the differentiating part does not change your steady state behavior because something constant differentiated is 0. So it really only changes the dynamics here. So if you say, okay, this magenta line is too much of an overshoot or is too slow, you add the D term, it gets a little bit faster. So one thing we're going to take a look at, we are in a time scale of 10 seconds now, because we're going to immediately see, if we add an integral controller, our system is going to get accurate, but slower. So applying an integral controller to that guy here, we are now seeing very nice. We have 100%. With 100%, we reach fully 100% of our input, right? So if I have an input of 1, the output is 1. Also, the disturbances are getting to 0, so this is pretty nice. However, the control gains are much, much lower. See, we've got 40 here, here's the maximum 1.5, and with a maximum of 1.5, we are very much overshooting already, very much oscillating. So there's a hard limitation on this control gain because we're adding too much, very much lag in our system by that integral. And you see that here, the time scale now is 5 times higher than we have with a pure proportional controller. And this is why pure integral controllers are rarely used, because they are so slow. They are slowing down your system. So next, we're going to fuse the P controller and the I controller. We're taking the speed of the proportional part and combined with the accuracy of the integral controller. And you see, this is the PI controller. Again, here I'm using this K star here because a PI controller, you can write it down here. The PI controller looks like this. It has this K star over S over TS plus 1 over S. So I'm not allowed to write K0 or KPI here because we have a free integrator, right? Okay, small detail here. Now we are fully accurate, again, like in the integral case. Also for the disturbance, so they get to 0. I just didn't want to increase the size here. And we are faster again, right? So we are in the time scale of 15 seconds now, right? So we are accurate and we are fast, right? So, okay, you could argue, well, we are still not in that time range here, right? Still, the integrator does you some harm here, right? It makes you pretty accurate, but still it's not perfectly fast. So if you say now, this guy is still too slow, you can add a differentiator here, right? Here, it looks very much the same. I'm using the same gains. I'm just adding a differentiating part, and suddenly we are accurate and fast, right? So this is actually the way you would also design a controller, right? To be fair, controller design is not like I'm looking at the system and I know immediately what controller do I need. It's an iterative process. Most of the time you really would say, okay, I mean, if you have a lot of experience, you immediately know that a proportional controller is probably not the good thing here. But you can always start with a proportional controller. You figure, I'm not accurate, I'm adding an integrator. I'm too slow, I'm adding a D term. I'm not saying that this answer here is better than this one. I'm just saying this one is faster than this one. If this already meets your specification, your boss tells you, right? It's totally fine. But this is the challenge we as engineers have to take. Okay, so this was for a proportional system. Let's take a look at the dynamics of an integral system. And this is actually the system we had before, right? It's an integral system with a first order lag. And we are now taking a look only at the proportional controller. What you see is that this guy is already accurate for D. reference tracking, but not accurate for the disturbance. You see, actually it's pretty bad for the disturbances here. Remember, a proportional controller for an integrating system is accurate for the reference tracking, but not for the disturbance attenuation. You can increase the gain, but it actually starts to oscillate pretty fast. So, because of the fact that we already have an integrator here, it does not make sense to add a pure integral controller. It will get unstable. 2 integrators for that systems, 3 integrators would be too much. But if we say, okay, this is oscillating too much, we can add a differentiator. So we use a PD controller. Let's do this. It gets faster, right? You should see the actually it's not getting that much faster, it's just getting better damped. See, the time scale is roughly the same. Actually, I could have plotted that with 5 seconds possibly, but the important thing is here, it's faster and it's better damped than the pure proportional controller. However, it's still not accurate here for the disturbance, right? So what do we do with the disturbance? Well, we definitely need an integral in our system, right? But we said, okay, a pure integral is not working. Why? Because two integrals are too much. Well, if you use a PI controller, we know a PI controller is faster than a pure integral controller. This actually is doing the job for us. So we add the fastness of the proportional controller and the accuracy of the integral controller. We fuse that and we applied it to our system, and suddenly we are having now an accurate system in the reference tracking and in the disturbance attenuation. But you see, it's actually pretty slow again. Why is it so slow again? Well, we now have 2 integrators, right? We have an integrator in the open loop from the controller, and we have an integrator here for from the system. Why is it actually working? Well, because the PI controller, if you go back one slide, the PI controller has a 0 here. And this 0 actually makes it possible that we actually can have 2 integrators in the open loop. So, well, what if we say this is too slow? Well, we add a differentiator, right? You add the differentiator, it gets nicely damped. The only drawback is here that this line gets to 0, however, it takes bloody long, right? So you could add another 0 here that would improve, but then we are out of the scope of PID controllers, and I really wanted to stay in kind of the, let's say, the space of PID controllers, because PID controllers really do a good job very often, and it's when you start doing control, to understand what a PID controller is doing and its sub-elements are doing is already enough, right? So if you want to still accelerate this guy, you can think of other methods which we're going to learn later, but yeah. Okay, that's actually it for this lecture. I'm 7 minutes short, but okay. I think I have some notes left, right? Yeah. So the steady state or stationary behavior we discussed on slide 42, which was this one, right? This was the steady state behavior. You can generalize this. So this is always true for proportional and integrating systems. So this is always true. However, the things we have discussed in the last 2 slides, they really are true for these 2 specific PD2 and IT1 systems. So the dynamic behavior really much depends on the system itself, right? If you add another 0, so if you take a PED T2, the answers will look differently. However, what the controller is basically doing, or what its elements are doing, how they are influencing our control loop, is staying the same, right? A D term will usually make your system faster, not always, but usually, right? So to analyze the dynamics of your system, you have to take a closer look. But to build up some intuition, I think it was worth looking at these examples. Okay, so where are we and where we are heading to. We know what the individual elements of a PID controller is doing. We know how they influence our stationary steady state behavior and the dynamic behavior. And we now know their roadmap, how to select as a controller structure, right? You have a certain problem, you have a certain system G of S, you now can think of different controllers, what you can use if you need steady state accuracy, if you need to speed up your system, and so on. What is still missing is, what are the numerical values of this controller, right? So, meaning that at this point you probably could say, well, I want to use a PI controller. You immediately know a PI controller has a form of, let's say, something like TS plus 1 over S. This is a PI controller. Still now the question is, what do you put in for these elements, right? So is this going to be 10? Is it going to be 1,000? Is it going to be 0.01? So this is the question we're going to answer next, depending on our system. And there are a lot of strategies in control, how to design or how to select these values. But this is the subject for the next lecture. I talk to you later and take care.